There we go. Welcome to lecture 18. Today we'll be talking about greedy algorithms. Greedy algorithms isn't so much a single algorithm as it is a collection of algorithms or a property of algorithms that you can have. The same way that you can have recursive algorithms and non-recursive algorithms, you can have greedy algorithms and non-greedy algorithms. We're going to go through some examples, work through some problem solving, and look at the definition of greedy algorithms, go through some more examples, and then go and finally end at when not to use greedy algorithms. It turns out that it's like knowing how to use greedy algorithms makes sense, and it's something we'll go over. Knowing when when greedy algorithm will produce the optimal best answer is a lot harder. So we're actually going to go at it in the opposite order. We're going to tell you when not to use greedy algorithms, and hopefully that'll help you build an intuition on when to use greedy algorithms. Okay, so let's dive right into it. Let's imagine we were at a restaurant. COVID is over. We can work at restaurants again, and 100% capacity. You don't have to worry about someone coughing at you and you being, at risk of being really sick. And we're at a restaurant that we have to serve customers at. Let's say we had N customers, and each customer will take X sub I time to serve. You can only serve one customer at a time. And for whatever reason, you're the only one taking care of all these customers, right? Let's just say it was a really busy day and everyone else was sick or something like that. And you want to minimize the combined wait time of all the customers. So if you're serving the first customer, all the other customers have to wait for you to finish serving the first customer. When you're serving the second customer, all the customers besides the first customer have to wait, and so on and so forth, right? Who do you serve first? Who do you serve after that, right? What's the approach that you should do to minimize the total number of minutes that everyone has to wait collectively? So for example, if we had customers that, in this case, we have 5 customers here. I'm going to label them 1 through 5. Previously, I tried to zero index and I realized I kept making small, dumb mistakes in lecture. So instead, we're going to index by 1, which makes it easier for me to explain things. So we have customer 1 here who has a wait time of 4, customer 2 who has a wait time of 2, customer 3 who has a wait time of 2, customer 4 who has a wait time of 6, and customer 5 who has a wait time of 1. Okay. And the question is, okay, how do we figure out which customer to serve first? Before we do that, though, let's just imagine how long does do we have to wait collectively if we served from left to right and then right to left? All right, so I'll give you about 30 seconds to answer this question. If we were to serve customer 1 first, then customer 2, and then customer 3, and then customer 4, and then customer 5, how long do you think it would take to serve all of the customers? Like, how long does every single customer have to wait, add it all together? Right, I'll give you 30 seconds down to think about it, and then we'll go through it together. All right, so if you have an answer, give me your best guess. If you're not sure, give me a question mark. This is like a really weird question, so that's why I'm taking the time to like ask you to try to figure it out. Okay, everyone's saying 15. Okay, great. You're all wrong. Let's go and look at this together, right? I haven't shown you how to compute this, which is why it's probably kind of confusing. So let's go ahead and figure this out. If we serve the first customer first, we're going to go ahead and say that first customer waited 0 minutes, but everyone else had to wait 4 minutes, right? Because they had to wait for the first customer to be finished in terms of being served. All right, everyone type 4 in chat if you understand where all of these 4s came from. They all had to wait 4 minutes each in order to get served, right? Now the first customer is done, we served that person. Now we serve customer 2, so they waited 4 minutes initially waiting for customer 1, but then didn't have to wait any longer because they were the next person up, right? Everyone else had to eat the cost of the 2 minutes that it takes to serve that person. And then if we keep going, we can see that there's a pattern emerging, right? We're going from left to right here. So the next person to be served is customer 3. Everyone else that is still in the restaurant still has to wait 2 minutes. And then customer 4 is next, but customer 5 has to wait 6 minutes extra in order to serve customer 4. And then lastly, customer 5 doesn't have to wait any longer at this point because they're the next person served, right? So we have 1 plus 4, right? 0 minutes for the first person, 4 minutes for the second person, 6 minutes for the third person, 8 minutes for the fourth person, and a whopping 14 minutes for the last person, right? So in this case, is that 14? Yeah, it's 14. Why 0 for the first instead of 4? Because this is the very first person that you have to serve. They didn't have to wait for anyone. They were the very first person, so they didn't have any initial wait time. Everyone else was waiting for the first person to be served, which is why they ate a cost of 4. And likewise, when you go to the next person didn't have to wait after the first person was just done serving, right? If they came at the same time, this scenario is saying, yeah, so this is when all the customers are already ready at the restaurant to be served. So you're already in a scenario where all of them are waiting for you. So then you have to pick one person to start serving, and you want to minimize the total amount of time everyone is waiting. All right, so if we add all of this up, we actually end up with 38, right? Because I've done this like 2 lectures now. It's the 3rd lecture. I finally memorized the number. This is 10, 18. Oh, wait, that's not how math works. 32. Yes, 32. Yeah. Someone's like, I said 40 something. Check the video. Play it back. Well, I mean, if you round up really heavily, I guess that would count as 40 something. Just playing around. It was a good intuition that you knew that this was going to be really expensive, which is the right move, right? So we know this is what happens when we go from left to right. All right, everyone type in 32 in chat if you understand where the 32 came from. Give me a question mark otherwise so I can explain it better, right? Again, if everyone understands this, then I can move on. If a lot of people are confused, then I should obviously explain it better, right? So let's go ahead and do from right to left. Now that you understand what we're supposed to be doing, right? I baited you a little bit, but now you're all engaged. How do we do right to left? What's the number that we get from there? I'll give you another 30 seconds and then we'll go through it together. It takes 32 minutes of physical time, or that's how much time waited by all customers combined? It's how much time it's waited by all customers combined. So this is almost like how long you wait is a bad thing. So we want to minimize that bad thing, right? Because if one person has to wait 6 minutes, but no one else has to, that's pretty good. But if everyone has to wait 6 minutes, then it feels worse for everyone collectively, right? So we're trying to find the collective wait time. In other words, we want to add up everyone's individual wait time together, which is where we got the 32 from. All right, so go ahead and type in your answer if you have it. What do we have here? Right to left. In this case, we know that everyone has to wait 1 minute at the beginning because you're serving the person on the very right. So customer 5, right? So customer 5 waits 0 minutes because they get served right away. Everyone else has to wait 1 minute. Going onward, we know everyone else has to eat a cost of 6 minutes when customer 4 is being served, right? Because everyone's waiting around while customer 4 is being served, and you can only serve one person at a time. So customer 4 takes 6 minutes to be helped, but everyone else is just waiting those 6 minutes. We keep going. Everyone has to accrue a cost of 2 at this point for customer 3. And then another cost of 2 for customer 2. And then customer 4 finally doesn't have to wait any longer. They are actually being served at this point. Customer 4 is just high maintenance. Yes. Yes. That is true. Customer 4 is very, very high maintenance. I would make some mean-spirited remarks about them, but I don't want to offend anyone. But, you know, sometimes you just have a very, very expensive or very fancy order, and it takes a little bit longer. We're not going to give them too much grief for it. If we add everything up, we end up with, in this first case, customer 1 now has to wait 11 minutes. Customer 2 has to wait 9 minutes. Customer 3 has to wait 7, and then customer 4 has to wait 1. If we add that all up, if we were doing addition, total would be, in this case, 28. right? So that's 10 plus 18 is 28, right? Someone said the mean comment. I was thinking, I don't like using that term for people who are high maintenance because I feel like there are plenty of people with that name who are actually really kind. One of my peers on my team, an EIR, is like one of the nicest, most intelligent people, well-read that you can know, and her name is Karen. And unfortunately, all of the mean Karens have ruined that name for all the nice Karens, which is lame. Anyways. So we see where 28 comes from here, right? And we can see that going from right to left is much better than going from left to right. But not by that much. Like we only got an improvement of 4 overall, right? Everyone still had to wait for customer 4, which accrued this cost of 6, which we know is kind of expensive. So now I'll give you about 20 seconds. What do you think is the best way to approach this? How do we pick the customers in order? What is the order that you want to pick them so that you'll actually minimize the total amount of time? So 20 seconds. What is actually the optimal answer here? All right, go ahead and punch in your intuition. What do you think? So people are telling me, let's serve the person with the least amount of wait time first, and then the people with the second least, right? And then the third least, and then the person who takes the longest goes last, right? Collectively, that makes sense because the person who waits, who takes the longest time to serve, is fundamentally going to cause everyone else to take a lot of time, right? By the way, sidebar, actually, this is fine for this problem, but in real life, there are times where you need a job that takes longer to start earlier, right? Maybe you need to serve someone who's maybe more important, or maybe a lot of people depend on that person, right? If you were serving, for example, Andrew, and he has to teach 160 people, and if he doesn't get breakfast, he's going to be a bad teacher. Then even if his order takes 6 minutes, maybe you need to serve that guy, right? Just saying. So don't disparage customer 4 too much. I'm sure that they have a really good reason for taking so long. Anyways, in this case, the intuition you all provided was that you want to serve the customers with the shortest wait times, as we can more quickly reduce the total number of people waiting, which will reduce the total wait time, right? So if we do this computation, we know that at the beginning, everyone only has to wait 1 minute because we're serving customer 5 first, right? And then we go ahead and serve customer 2 next. And everyone besides customer 5 who has already been served and customer 2 who's currently being served eats a cost of 2. From there, serving customer 3. From there, serving customer 4. And then lastly, serving customer 1 and then serving customer 4 after that. Yeah, for those of you who are saying the solution is to hire more people, I agree with you, but sometimes scarcity is a thing, right? So if we add everything up, 0 for customer 3, I made a mistake somewhere. Where did I make that mistake? Customer 3, yes, you are correct. Thank you. I love it when people help fix my typos. Sometimes it's really hard to answer and fix everything on the fly, so thanks for playing along. So in this case, we have 9. And if we add them all up, total in this case is really small. It's just 18, right? Is that how math works? That's 12, 13, 15. Yeah, okay, nice. So total here is way cheaper than either of the options we had before, right? So essentially what we're doing here is going ahead and sorting the customers by the shortest wait time first. So functionally, what we would have to do in Java would be to make an array of pairs where we have, for example, 4, 1, 2, 2, 3, 2, 3. So the first argument is the first element in the pair is the actual wait time. The second element is the customer that we're talking about, right? So in this case, we have 6, 4, and then finally 1, 5, right? We would sort this And if we sort it using, for example, merge sort, or maybe if you're really fancy, you can find some way to make radix sort work. You would be able to do this in an efficient amount of time. So O of in log in for merge sort, or O of in for radix sort, if you could figure out radix sort. I'm not actually convinced that radix sort would work here, which is why I'm a little bit hesitant to say that this would be an O of n algorithm. But someone who has more time to think about it than me, like, go ahead and check it out, see if there is actually a way. But essentially, after sorting, we get this, and then we would just collect all of the customer IDs, indices here, and we would get at the end of the day 5, 2, 3, 1, 4, right? Which suggests that we serve customer 5 first and customer 4 last. And as I just mentioned, the runtime here, where n is equal to the customer length, should be n log n. Ignore this for now. Again, I'm not sure if radix would actually work, but we know for sure that we can use something like merge sort to sort a list of n elements. In this case, n is the number of customers we have. And for sure, the rest of this code doesn't take as much time as the sorting does. So we end up having an n log n algorithm overall. All right. Give me a 1 in chat if you feel good about this example. Give me your questions or question marks if you have anything you wanted to ask at this point. All right. So we just went over our first official example of greedy algorithms. Not the first one we've seen, but the first one that is in our greedy lecture. So a greedy algorithm, as the name suggests, is essentially an algorithm that always makes the choice that seems to be the best at that moment. This means that it makes the locally optimal choice in the hope that the choice will lead to a globally optimal solution. All right, so I'll give you a couple of seconds to digest that before I move forward. So essentially, we want to say that greedy does not plan ahead. It doesn't look into the future. It also doesn't really look back. We don't look at the past. We don't look at the future. We just assume that by picking the next obvious thing, we will eventually end up with the correct and optimal solution. Right? So there are times where greedy can produce a solution that's pretty good or at least valid, but not necessarily a solution that is by definition the best possible solution. In other words, this approach only works for some problems. So the skill that we're building in lecture and in homework this week is recognizing when a greedy approach will work and knowing how to pick the next obvious thing. Cool. Let's take a look. By the way, blue slide. It feels like we haven't seen one of these in a while, but blue slide, super important. Make sure you keep track of this. This is how the basis of your knowledge works, right? You have to start by memorizing something, and this is one of those things. So example number 2, let's imagine we had a lecture hall. What's like a famous lecture hall that you always have to go to on GSU campus? Does anyone have one? For Berkeley, it would be 155 Donnell. Kell Hall, hall number 4. Langdale, Adderhold. I don't even know the names. Fair. Langdale seems like the consensus. So let's imagine we were booking lectures for Langdale, and we had to maximize the amount of lectures we could put in a day for this lecture hall. Each lecture has a start time, S sub I, and a finish time, F sub I. In other words, a start like 1 p.m. and a finish like 3 p.m. We want to maximize the number of lectures we can schedule in this hall. Lectures can't overlap, right? You can't have a lecture start at 1 p.m., end at 3 p.m., and then have another lecture in the same hall that starts at 2 p.m., because then they would overlap. So you need to pick which lectures to schedule, and we assume that we get a list of lectures sorted by their finish time. So here's an example. I'll give you 15 seconds to think about what's the maximum number of lectures we want to book. Conceptually, maybe let's say that we get a speaking fee or a facilities fee every time we hold a lecture. So the more lectures we hold, the better. Conceptually, that might be a reason why we're doing this. More greed, right? I'll give you 15 seconds to think about which lectures you want to pick and what's the overall number of lectures you get to book given this example. Again, we're trying to figure out which lectures we're going to book here to maximize the total number of lectures we want. All right, which lectures do you pick and how many are there total? All right, a lot of people are punching in that we want the first lecture, right? Lecture 1, followed by lecture 2. Obviously, they don't overlap. We end at 2 p.m. here, and then we end at start at 3 p.m. here. To be clear, like this lecture 1 starts at 1 p.m., ends at 2 p.m. This lecture 2 starts at 3 p.m., ends at 4 p.m. This lecture 3 starts at 12 p.m., but ends at 6 p.m., which is a really long lecture. 4 p.m. Lecture 4 starts at 5 p.m., ends at 7 p.m., so on and so forth, right? If there are ties, we break by shorter lecture. So that's why lecture 5 starts in the list earlier than lecture 6, even though they both end at 9 p.m. Okay? Who's holding a lecture at 9 p.m.? That seems a little bit excessive, although I've heard stories. So we know we want to pick 1, 2, 4, and 5 here because that maximizes the number of lectures we're allowed to pick. In this case, we are able to pick lecture 1, and then from there we pick lecture 2 because it doesn't overlap with lecture 1. We want to skip lecture 3 here because it takes a long time, and if we picked it, we wouldn't be able to book 1 and 2. We want to pick 4 here because it doesn't overlap with lecture 2. That's cool. We want to pick 5 because it doesn't overlap with lecture 4. And then lecture 3 overlaps with, in this case, 4 and 5, so we don't pick that. Right? So total, we have the total number of lectures we're able to maximize in this case is 4. Right? Now, the question I have for you is, how did we make this way to pick? I put obvious here in quotes. It's not really obvious. It actually requires a little bit of thought. So let's instead say, instead of obvious, what is the greedy approach, the greedy way to pick here? What is the way we can maximize the amount of lectures we want to pick based on some choice that we have to make that doesn't rely on planning ahead or looking back at what we've already picked? Right? Mostly planning ahead. Looking back is like mostly okay, but we don't want to spend too much time looking back. All right. I'll give you another 15 seconds to come up with an answer. Again, there's not entirely obvious, so you might get it wrong, and that's totally okay. I just want to see everyone's intuition. And this is another chance for me to bait you all and prove that there's a better answer than their initial intuition, right? That confusion, that sense of confusion, or the sense of, oh, wait, this isn't right, what I just said, helps you remember this a little bit deeper. All right, go ahead and punch in chat if you have it. All right, everyone is picking. Pick the lectures with the shortest times first. Pretty much all of you are. So I get to grin now and say, here's a counterexample to what you just said. Let's say we had lectures 1, 2, and 3. Lecture 1 starts at 0 and ends at, let's say, 6. Lecture 2 starts at 5 and ends at 7. And lecture 3 starts at 6 and ends at 7. Y'all just told me to pick the smallest lecture, the lecture with the shortest time first, right? So I picked this lecture. I picked the shortest lecture. That's the lecture you told me to pick. That means we can only pick lecture 2, right? Which is a problem. What should we be picking? What should we be picking? Go ahead and type in chat. What are the 2 lectures that we could actually pick here that helps out? We could pick 1 and 3, right? 1 and 3 is what we want to pick. If we just pick the lecture with the shortest time first, we end up in this weird position where lecture 2 dominates the space and it overlaps with 2 other lectures that we could have picked instead. Even though lecture 1 had like a 6-hour lecture. I don't know what that lecture is all about. Maybe it's the extended Lord of the Rings cut and they're showing it in Adderhall. But even though we have longer lectures, as long as they don't conflict with other lectures, who cares? We can book that space, right? So the intuition here is we can book longer lectures as long as there aren't any conflicts with any other lectures. We want to use the dead space because if there are no other lectures at that time, even if the lecture's super long, like we don't care. Let's just use the space, get our facilities fee, and then make bank, right? So here, What do I mean by dead space? I mean that right now, let's imagine we had a really long lecture, but no other lectures need that time. Like, let's say we had a morning lecture that goes from 8 a.m. to 12 p.m., but there are no other lectures that have the morning lecture. Then, of course, we want to book that morning lecture, even if that morning lecture is super long, right? So our intuition isn't so much to pick the shortest lecture. What we want to do is to pick the lecture that ends the earliest. All right, so let me say that really carefully. We pick the next earliest ending lecture that doesn't overlap with the previous lecture picked. All right, the intuition that we want to cultivate here is that we went and optimized something. We picked here, instead of having like the minimum wait time or the shortest lecture, we picked the earliest ending lecture as long as that lecture didn't overlap with the previous lecture that we picked. All right, type in earliest in chat if you feel like you're good here. If you feel like the intuition in purple doesn't seem too far-fetched, we're going to look at an example, and then we'll try to build up the intuition a little bit more, because I think some people are still a little bit confused, right? Okay, most people are feeling a little bit good about this, so let's go ahead and move forward. I'm going to move these a little bit up here, and make sure we have some space for the code that I'm about to show you. So in this case, here's the code that we actually want. We have, this is from your textbook, and this is why I don't use examples from your textbook super often. The code is a little bit, requires a little bit of explanation. To be fair to them, they explain it better in the book. So I'll just go ahead and explain what each of these variables mean. We have a greedy activity selector. So in this case, the activity is lecture, which takes in two arguments, an S and an F. An S is an array of start times, so all of these in an array. And then F is an array of end time, so all of these in an array, right? S for start, F for finish. Now we go ahead and we create a capital A here. A is equal to the set of lectures we pick, all right? And then A sub 1 is equal to the first lecture, right? So lecture 1 is being picked here when we say A sub 1. K is going to be equal to the last lecture we picked. So in this case, if we always pick the first lecture no matter what, then we are setting K always to be 1, right? Because we're indexing from 1 so that Andrew doesn't get confused. Also, the lecture, or sorry, the book always indexes from 1 a lot of the times. So it's just nice to follow that convention just for the sake of sanity. And we're going to go through all of the other lectures from there. M is going to be indexed into lectures start and stop times, right? Start and finish times. So an index into F and an index into S here. And we're saying that for all of the numbers, sorry, all of the start times, we're going to look at the current lecture, see if the start time is after or equal to the end time of the previous thing we just picked. And if it is, we can add it to the set of elements that we are collecting, the set of lectures we're collecting, right? So I'll write that down here. If the current lecture's end time is greater than or equal to the previously picked lecture's start, then we can pick this lecture too, right? Which is why we say A is unioned with the set of A sub M. In other words, we're adding the current lecture A sub M into the set of lectures that we're picking. We're adding it to A. And we're setting the previous lecture we just picked now to the current index, which is the M that we just processed. All right, let's go through the example and try to play through how this works. Someone is asking, hey, does this work all the time? It turns out it's always going to work, and I'll explain why in a little bit. All right. Is there a reason why we assume the first one should always be included? That's you are all asking such good questions. I'm literally going to answer them in about 3 minutes. Let's walk through the example first, right? I'm really happy because y'all are proactively like thinking about it, which puts a genuine smile on my face. All right, so let's go ahead. We know we have to pick lecture 1, right? We are forced to pick lecture 1 because that's literally just what the code tells us to do. So let's check that off. All right. Then the code is saying go through all of the other parts of the lecture. So we're going to go and iterate through all the other lectures going forward and look at all of them one at a time. So M starts at 2, which means we look at lecture 2. Type in 2 in chat if you're with me so far. We picked lecture 1, which is why there's a green check mark. Now we're at lecture 2 because by definition, we're just looking at the rest of the lectures one at a time. Now we look at the start time of lecture 2, which is what the S of M, S of M, I think, or S with M in the square brackets. That's what that means. And we compare it to the finish time of the previous lecture we just picked. In this case, we only had one lecture, the first lecture that we picked. And so we check, hey, is the start time of the current lecture greater than or equal to the end time of the previous lecture that we picked? The answer is yes, right? 3 is greater than 2. So we go ahead and pick 2 as well. We do the same thing now, and we set K now from 1 to 2, right? So now we set that K is equal to 2. And M now is equal to 3, right? So now we're looking at lecture 3. Lecture 3, we do the same logic. Is the start time greater than or equal to the previous lecture's end time that we just picked? Yes or no? Of course not, right? Because 0 is not greater than or equal to 4, so we don't pick this one. We cross this one out, right? We go ahead, we do the same logic again. We check to see now that M is now equal to 4, right? If M is equal to 4, then we check to see if the fourth lecture has a start time that's greater than or equal to the previous lecture that we picked. Right now, K is still equal to 2, so we're looking at lecture 2's end time and comparing it with the start time of lecture 4. And it's good. So we go ahead and pick that. We move on. Now M is going to be equal to 5. We do the same check. 5 against 4 now, because lecture 4 was the last lecture we picked. I'm not going to update the numbers here because it takes too much time. And we check this one off as well, right? We do the same logic for 6. We realize that 6 is not going to work because the start time here does not compare favorably to the end time of the last lecture we picked, right? And that concludes our algorithm. And it gives us the exact same output that you all instinctively or intuitively picked when you were working it out by hand, right? So here we go. Someone asked, what if we swapped lecture 2 and 5? That's impossible because we assume all lectures are sorted by finish time. This is going to be a big deal, right? So my first question for you is, why does this work? Why does this actually work? Well, let's go on the top right here. I'm going to do it in blue. Why do we pick the first lecture always? How are we guaranteed that this will always produce the optimal result? Right? Some of it is because this is sorted by finish time, but I'm going to give you all about 30 seconds to just take this all in. If you have questions, ask. And see if you can come up with some reasoning, some maybe even a mathematical proof for why this will always work, why we should always pick the first lecture, and why we are always guaranteed that this approach, this algorithm that I have on the bottom right here, will always produce the correct result. You lost me at math proof. Yeah, we're not actually going to cover the mathematical proof, which would be a proof by contradiction, where we assume that we had an alternate optimal solution, and then we prove that that optimal solution. Anyways, we're not going to talk about that in great detail. We're going to give you the intuition, and then we're going to move on, because I know that a lot of you are scared of math, and I want you to focus on the programming and computer science part of it. The math is actually genuinely important. And it hurts me inside that I can't like walk through the proof. But this class, at least based on the design we've approached it, is not going to be proof based. So we're not going to harp on that too much. All right, so you should be taking this time answering the blue questions on the top right. I'll give you another 5 seconds to think about it while I set up for kind of an example or explaining afterwards. All right, go ahead. What do we have? What do we have here? What do you all think? Okay, we're getting a lot of question marks in chat. I love it. This is exactly the response I was expecting, and I think it's totally fine, right? Some of you have some arguments that relate to how it's sorted by the first finish time, which is getting at the right direction. But we want to be able to give a little bit more reasoning than that. I think some of you have started to add a little bit more like detail into it. But let's go ahead and take a look, all right? Let's imagine a couple of things. Let me go back here. And we're going to remove the code for a second and just think about this example here, right? We know we want to pick the lecture with the earliest end time, as long as it doesn't conflict with the previous lecture picked. All right, that was the idea. I'm going to keep it on the bottom right here so that you don't forget it. And then we're going to look at some examples of what's going on here. All right. So let's go ahead and imagine for a second two scenarios. If we pick not the first lecture, one of two things will happen, right? Let's imagine we pick some other lecture apart from the first. All right. Give me a yes if you're with me. We're imagining a scenario where we don't pick the first lecture. Okay. So here's where the slightly mathy thing or the slightly logic inducing thing comes into play. There's two scenarios we could have. Either the lecture we picked will conflict with the first lecture or it won't. Right? So let's say that if it does conflict, there's going to be a case for that. If it doesn't conflict, there's going to be a case for that as well. All right? Let's just think really carefully here. If we have a case where it doesn't conflict and we pick the second lecture, right? And, you know, either it's the second lecture or maybe a later lecture. Why wouldn't we pick the first lecture here? Right? If we pick a lecture that's not the first lecture and we have some other lecture start us off, but there's no conflict, then why wouldn't we pick the first lecture anyways? We would just book that dead space like we said before, right? We want to use the space if it's not being used by any other lecture. There's no conflict, right? So everyone type in Y in chat if you understand the argument that if it doesn't conflict, we should definitely pick it, right? So I'm saying if we don't pick the first lecture, imagine we picked any other lecture down the road, then if it doesn't conflict, we should definitely just pick the first lecture anyways. Like if we want to maximize the total number of lectures booked and there's no conflict between the lecture we picked that is later in the day, ends later, then we should definitely pick the first one anyways, because that just gives us a +1. All right. Now, if it does conflict, there's two flavors, right? There's two scenarios inside of the conflict scenario. Either one of two things will happen. Either we'll still be able to get the same number of lectures booked, or the lecture we picked will force us to pick less lectures overall. All right. So let me give you an example of what I mean. All right. Let's go ahead and take a look here. Let's imagine that we were looking at this example and we were looking at the doesn't conflict case. We're looking here in green. We pick two. We don't pick one. We just pick two, right? If we pick two here, lecture 2, what are the other lectures going forward that we would pick? We ignore one for now. What are the other lectures down here that we pick? Go ahead and type in chat. Follow with me now. We would want to still pick 4. And we would still want to pick 5, right? And everyone feels good about that. Like those are the obvious ones. This is from exactly the example we gave before, right? And at the same time, it doesn't give us the maximum number of lectures booked. We could still book lecture 1 without any consequence if we wanted to, right? So why wouldn't we? Right? So that's the argument for the not conflict case. Let's go ahead and look at the conflict case. So now let's imagine another world. If there's a conflict, Let's imagine that we had a conflict that looks like this. We have 1, 4 here. So, sorry, 1 second. Let me write this in a different color. So this is in red. The conflict case is always in red. We have 1 instead of 3 here. So we have 1, 2, and 1, 4. We see that this conflicts, right? Now, here's the case. We're in the first case here. What are the 2 valid ways that we could get 3 lectures? We know we can only get 3 lectures at this point. All right, just think about it for yourself. I promise it'll be obvious in a little bit, one way or another. But think, what are the 2 different ways we could book lectures? The 2 different sets of lectures we could book that would end up with 3 lectures total. Go ahead and type in chat if you have it. We could pick 1, 4, 5, right? Or we could pick 2, 4, 5. And that's all we could do, right? If we picked 1, 4, 5, well, if we picked 1, 4, 5, then we would still have 3 lectures. So it doesn't really matter if we pick 2, 4, 5 versus 1, 4, 5, but picking 1, 4, 5, we're guaranteed in that case to have at least the same number of lectures booked, right? Now, here's another example of the conflict case where we have an overlap here. Let's say we start at 3 and end at 5 here. Okay. Now, I'll give you 30 seconds. We don't pick 1 and we pick 2 instead. If this happens, what do you think is the answer we could get that would be the best if we had to pick 2? I'll give you another 30 seconds, and then I'll answer the question in chat, which I know people are asking. All right, what are the lectures that we have to pick if we start at 2? We pick 2. What else do we pick? Sorry, this should be a 6. I lied. This should be a 6, not a 5. That's why people are confused right now. This should be a 6, not a 5. That was a mistake. Let's try that again. So I picked 6. Go ahead. I picked 2 here, and then we're forced to pick 5, right? We can't pick 4 now because there's an overlap. We don't want to pick 6 still. So if you started with 2 and you didn't pick 1, you would be stuck in this scenario where you had to pick only 2 and 5. And then if we picked 1, well, if we picked 1, we can't pick 2, but we could pick 4 and we could pick 5, right? So again, the lecture we picked will force us to pick less lectures overall, is the argument being made. Now, someone asked in chat, and I know it was asked several times, and I've been ignoring it up until now. What if lecture 1 took really long? Well, there's 2 cases for that. Either lecture 1 took really long, and if it was a long lecture that had a long end time, let's say this was 9, right? If this was 9, then it wouldn't be the first lecture. If this was 9, then this entire thing should be at the end because we're sorting the lectures by finish time. Otherwise, the only other time where the lecture could be really long is if this was like a start time that was really early. So let's say this was like -11 instead, right? And so -11, which would be some unholy number of hours in the morning, and then goes all the way to 2 p.m. somehow, would be the start time, and it wouldn't conflict with anything else. So of course we would still book it. Could I do this with the start time? I don't think it works super well with the start time, but you might be able to make it work. I don't know offhand. This is the canonical way to think about it. All right. So that was the argument. The entire argument is that if we don't pick the first lecture, one of 2 things will happen. Either it will conflict with the lecture we actually picked, in which case we'll either be able to get the same number of lectures booked with the new lecture that we picked instead of the first one, or we'll actually be stuck with less. Otherwise, if it doesn't conflict, then we should just book the early lecture no matter what, because there's no conflict, and therefore we just get free booking, right? In case where lecture 2 is 3 to 6, why wouldn't we pick that? The start time of lecture 2 is more than the finish time of lecture 1. I might have made a mistake. Yeah, I should have said in the conflict case. Yeah, you're right. I should have said 1 to 5 here. That would have been correct. Sorry, I was doing the example really, really fast. It should have been 1-5, not 3-5. That's my bad. Thank you for calling that out. All right. That was a lot of words to say at once. Let's go ahead and take a breakdown. Actually, before that, let's go ahead and look at greedy algorithms. So other algorithms that we've seen that are actually greedy, following the same principle, is this idea of graph algorithms that we've seen in the last couple of lectures. Dijkstra's was an algorithm where we picked the next node that was unvisited and that was closest to S based on distance. And then we processed their neighbors, right? And we just did that over and over again. Each step, we would pick a new George, we would crown that George, we would look at the neighbors, and then we would do that over and over again, right? All hail King George. Then we had prims, which was from last lecture, where we just picked the cheapest unvisited node to visit, right? And that turned out to be pretty good as well. In this case, the cheapest unvisited node to visit allowed us to grow our minimum spanning tree one node at a time until we eventually had all the nodes. And lastly, we had Kruskal's, which we picked the next cheapest edge that doesn't cause a cycle. In this case, it's the same principle where we're just doing the next obvious thing and trying to maximize the local benefit in the hopes that we'll end up with the correct answer, the most optimal answer at the end, right? So in general, a greedy algorithm will try to maximize benefit or minimize cost at each step, right? So we're trying to maximize benefit. In other words, pick the next unvisited node that's closest. Pick the next cheapest unvisited node to visit. Pick the next cheapest edge. So we're minimizing costs in all of these, right? We can also maximize benefit for scheduling the lecture hall by trying to maximize the number of elements, the number of lectures we can book by booking the earliest lectures first. Another example of minimizing cost is this idea of, for example, minimizing the total amount of wait time by picking the customer that has the least amount of wait always. All right, let's go ahead and take a 5-minute break and then we'll come back. So we'll come back at 6:50. And then in the last bit, we're going to talk about when to use greedy and when not to use it, right? For those of you who are asking, hey, did we see some previous algorithms that were also greedy? One other example is selection sort. If you remember, we just repeatedly picked the smallest element that we could each time, the next smallest element, and we built up a sorted list from that, right? So again, we're on break. We'll come back in 5 minutes. Please take a look at my cat and say nice things about him, although he's very close to this cat in the comic on the left. He's kind of a jerk sometimes. If you have any questions about greedy algorithms or other examples or other things you want to know about the class or anything else, now's the time to ask. We got another 4 minutes to just chill. I know we talked about a lot of things all at once, so feel free to just relax your brain if you prefer that. Which algorithms are non-greedy? I mean, a lot of them, right? Like, we'll talk about exactly what the properties of a greedy algorithm is right after the break, and you'll be able to maybe more readily identify them as you go. Any movie or show recommendations so I can forget to watch them? Last section, we were talking about how Queen's Gambit was pretty dope, which I agree with. It's like 7 episodes on Netflix. It's very intense, both from a psychological and emotional and philosophical like way of looking at it. It's about a chess player who's female back in like the 20th century, where no one thought that women could play chess as well as men. So she goes around and kicks ass and takes names, but also deals with her own like internal trauma. It's a very, very intense show, I think, and you might enjoy it if you like that sort of drama. Anyone watching Attack on Titan? I have not started last season of Attack on Titan. I'm like way behind. I'm like 3 seasons behind. I'm watching Wonder Egg Priority, and I'm also watching um, Jujutsu Kaisen, which I think is surprisingly good. It's like better Naruto, which is I think the point of it. Ooh, someone just watched Serial Experiments Lane. That is another very intense psychological like metacognition type anime. You don't have to watch anime. There are plenty of other cool things to do in the world. Anyone go on any hikes or rock climbing or went out to a park, went biking? Or maybe bake something yummy in their kitchen recently? Drove 2 hours to Brasstown Bald. Cool. Hope it was worthwhile. Just to spend 15 to 20 minutes there. Hopefully that was enjoyable. I don't know. Just moved to a new house. I hope your move went smoothly. All right, we're gonna push a little bit early here and get back on track because I want to make sure we cover everything. Let's go ahead and take a deep breath. Stretch one last time if you haven't already. Make sure you push your shoulder blades back and get good posture again. Type in yellow in chat if you're ready to start again. We have a yellow slide. It feels like a long time since we've seen one of these. All right. So as I said before, like when we were talking about the approach for scheduling lectures, it was really hard to prove why this would always produce the correct answer, right? I kind of gave you a very hand-wavy explanation and worked through some examples, but it wasn't a formal mathematical proof. However, proving that something shouldn't be a greedy approach, like that we shouldn't use a greedy algorithm here, is way easier. So let's go ahead and take a look at that. Two properties of a problem need to be satisfied before you can use greedy. One, the problem needs to be able to have an optimal substructure. Now, this is just a fancy way of saying that the problem should be able to be solved recursively. So number one is an optimal substructure. An example of that is, for example, when we're talking about serving customers, if we serve the first customer here, then we have the rest of the customers in an array, and we've made the problem smaller, and we just solve the same problem again by picking the smaller customer, the customer with the least waiting time, rather. And then we look at the smaller array that results from that, and we just do that over and over again, right? So recursively, we're going through a sorted list of elements based on the shortest waiting times. And that's one way to say that we have an optimal substructure. Now, the other example, though, is this idea of the no regrets or YOLO principle. It's a technical term. I'm sure you've never heard of it. You make the choice that seems the best at the moment, and you solve the subproblems later. You don't care about consequences. And the hope is that if you can still reach the optimal solution there, then you will have satisfied this property, right? So the idea is that you have no regrets. You don't reconsider your earlier choices, and somehow there are no consequences to your actions, right? That's how, if both of those are satisfied, we can use greedy. Now, if the first one isn't satisfied, then you can't use greedy at all, because if you can't solve a problem one step at a time and make the problem smaller and smaller, one choice at a time, then you can't use the greedy approach, because by definition, that's what greedy does. But if the second one is not satisfied, if the greedy property isn't satisfied, it turns out we can still use the greedy approach. We just won't get the optimal answer. We'll get an answer that's worse than the answer that we actually want. All right. So there's a lot of problems where you're trying to find a solution, and you can have all different kinds of solutions. Some are really good and some are really bad, right? Like, for example, in order to sanitize your shirt, a really good solution is to put it in the dish, into the washer and then the dryer. A bad solution would be to put it into the dishwasher, or a really bad solution is to set it on fire. So ideally, we want to go ahead and only solve problems using the greedy approach when the problem itself actually can get an optimal solution by picking greedily each time, right? In other words, if you want to prove that you shouldn't use a greedy algorithm, all you have to do is come up with a counterexample. An example where by using the greedy algorithm on a certain problem, that problem will not come up with the algorithm that you use that's greedy won't come up with the correct solution, the optimal solution. All right. Okay, so let's go ahead and take a look at a concrete example here. Let's take a look at two separate problems that are very, very similar, but just by changing a small part of the problem, you can use greedy or you can't. All right, so here's problem one. A vending machine has pennies, nickels, and quarters. For those of you who are not in the US and don't know what these mean, this is a 1-cent coin, a 5-cent coin, and a 25-cent coin, right? Some of you might scoff and say, oh, everyone should know what that means. I've had students who, come from different places who might not know offhand, and that's not a big deal, right? No one uses coins anyway. So if you didn't learn on your way here to the United States, like that's not a big deal, right? So we know that the pennies cost 1 cent, the nickels cost 5 cents, and the quarters cost 25 cents. You're a vending machine. So like you dispense soda, but you also dispense change. If I give you like a quarter, if I give you $1 and I only spent 75 cents of that dollar, I expect to get a quarter back, right? Or maybe I get 25 pennies back, or maybe I get 5 nickels back, right? What we want to do is find the way to give me back change in the fewest amount of coins, right? And we want to do it so that we return the exact change. So the second problem is literally the same problem as the first problem, except instead of having nickels, we have dimes. So dimes instead of nickels, and it's the exact same prompt otherwise. It turns out one of these problems can be solved using a greedy approach and the other one can't, even though this is fundamentally the same type of problem, right? Give me a change in chat. Give me a change in chat if you feel like you understand the premise. Keep your coins. I want change. All right. Hopefully this is making sense, making a lot of sense, or I guess in this case, making as little sense as possible. Someone laughed at my joke. All right, so let's take a look at the first example. A vending machine has 1-cent coins, 5-cent coins, and 25-cent coins. Let's go ahead and say that n is equal to 31. What would be the optimal number of coins that you would want to use here? I'll give you all 10 seconds to think about this. How many coins would you want to use in the best case? Right? This isn't meant to be super scary. I just want everyone to make sure that they actually understand what's going on. Go ahead and type in chat if you have it now. Right? We want to use 3 coins. We want to use one 25-cent piece, one 5-cent piece, and one 1-cent piece, which would give me 31 in total, which is 3 coins used, right? Now, conceptually, if we want to do this in a scalable way, if we want to generalize this, what would be the greedy approach? Go ahead and take about 30 seconds to think about this. How would you describe this using words, right? What would be the greedy approach here if you wanted to actually describe what you're doing by hand? And maybe, think about an example, like let's say if we want to use n is equal to 49 here, right? If n is equal to 49, what would we do for a greedy approach? Okay, type in chat if you have an idea or a guess. Type in question mark if you're not sure. All of you should be using your intuition, right? You shouldn't have to be too hard stuck on this. But the idea here is use the biggest coin as much as you can, then use the second biggest coin as much as you can, etc. Right? So in this example, for n is equal to 49, we're going to go ahead and use the quarter first, right? We're going to use a 25-cent piece. If we use a 25-cent piece, then how many cents left do we still have to make change for? Go ahead and take 5 seconds and then type in your answer in chat. All right. If we use 25 cents and we're trying to make change for 49 cents, how much do we have left to make change for? We still have, 25 to make change for. Obviously, in this case, we can't use another 25-cent piece because then we wouldn't have exactly dispensed the right amount, right? We would go into the negatives, so we don't want that. So we're going to use 5 here, right? So in this case, n is equal to 19. We'll use 5 again. N is equal to 14. We'll use 5 again. And we're going to keep doing this for a while, right? We're going to use 5 here. And then we're going to use 5 again. Until eventually we get here. And at this point, what do we do now? Go ahead and type in chat. What's the next step that we use? We have to use the pennies, right? We're stuck just making this change go down as one at a time, right? So n is equal to 2, n is equal to 1, and then we're done. Right? So overall, the number of coins we have to use, 9 coins used total. And that's the approach we have, right? So conceptually, why does this work? Like, why does this actually seem to work? And, I'm telling you right now that this actually works from a greedy point of view. We're actually going to get the correct answer all of the time. Someone said it's incorrect. Give me a counterexample. What's a counterexample where we want less coins, but this will give us more coins? If you find one, let me know in chat. I'll be reevaluating my life choices if you find one. I did use 5 nickels. Did I just do the math here wrong? 1, 2, 3, 4, 5. One of these should be 1, right? That's correct. Yeah. Sorry about that. Thank you. Okay. I don't reevaluate my life choices, but I reevaluate my ability to type and speak at the same time. That was a typo. Thank you for catching it. All right. So go ahead. Why do you think this works? Does anyone have any intuition? You can always type question mark if you're not sure, but go ahead and punch in. What do you think happens? Why do you think this actually worked out? So we have an optimal substructure, right? When we make the problem smaller, then we still have a number of coins a number that we want to make coins for, right? Make change for. We've reduced the problem. So the optimal substructure is definitely there, because if we use a coin, we make the n go down by some amount, and then we use a coin again, right? So this is where optimal substructure comes from. That's not the important part. The most important part, though, is that greed works here, because each coin can be represented, each collection of coins can be correctly represented by a larger coin. All right. So there's this really interesting concept where you can have 5 nickels equal to 1 quarter, right? And that just perfectly works. And then 5 pennies equals to 1 nickel, and that just perfectly works. And so if we are able to reduce the number of nickels by using a quarter instead, then we obviously always should, right? So let me say that again a bit slower. If there is a world where we have 5 nickels, we can always reduce the number of coins being used by using a quarter instead. So if we go ahead and try to use as many quarters as possible, then that will overall reduce the number of coins we're using, because the alternative would be to substitute that quarter with either 25 pennies or 5 nickels. All right. Let's go ahead and move on. I'm going to ignore that bad joke someone just made in chat, because I made that bad joke first, so you don't get any credit for it. Let's go ahead and look at the counter, right? We now look at a separate universe where the vending machine has pennies, no nickels, dimes, and quarters. So just to be absolutely clear here, we have 1 cent here, we have 10 cents here, and we still have 25 cents at the end here, right? Now, here's my question. Can you come up with an example? What's a counterexample where the greedy approach fails? That's what I'm really asking here. I'll give you all 10 seconds, no, 30 seconds to think about this. And just to remember, the greedy approach will be pick the largest coin to use it as much as possible, then pick the next largest, repeat, right? That was the greedy approach. We had these steps. I'll give you another 20 seconds to think about what is a counterexample where using the number of coins and picking them in this way will not end up with the least number of coins used. All right, go ahead. Type in chat. What do you think? All right. A lot of people are typing in question mark, but there are some suggestions, for example, 30 or 31. So let's just go ahead and consider when n is equal to 31, right? If n is equal to 31 and we were using this greedy approach, I'll give you all 15 seconds. What coins are we going to use for the n equals 31 case if we do it greedily? What's the first, I'll just give you another 10 seconds. Just think about it for yourself. We use the greedy approach to try to partition 31. Go ahead and punch in chat if you have it. What are we using here? Right. Remember, we don't have nickels anymore, so we have 1/4. We have 1/4 and then 6 pennies, right? We don't have any nickels. You can't use any fives anymore. We only have 10 cent, 25 cent, and 1 cent, and therefore we can't use the fives anymore. Now, this kind of sucks because the actual answer, like greedy answer, gave us this, which is 6 coins. The actual answer, the best answer is what? 4 coins? Because you would want to use 10, 10, 10, and then 1, and then we're done, right? So fundamentally, we know that the greedy approach doesn't work because we can come up with a very simple example where when we try to use the greedy approach, that didn't work. The actual answer is a different number than the answer we came up with, right? All right, so would greedy work here? Give me a yes or no in chat. What do you all think? No, right? Because we just proved it. How did we prove it? Because we have a counterexample. We picked a counterexample. This counterexample here showed us that in this case, greedy is not always good. It's good sometimes, and you have to pick and choose your battles, but in this case, it's kind of lousy. And why doesn't this work? Someone already mentioned it in chat. Remember, before we had this property where each coin could be replaced by a fixed multiple of the other coin, right? So for example, 25 is equal to 5 nickels. Well, if we didn't use a 25 cent piece, if we didn't use 1/4, then we would be stuck just increasing the number of nickels, the number of coins we use, because we would be forced to use nickels, right? If we didn't use the quarter, we'd be forced to use more nickels, right? Increasing the number overall. This is before. Now there is no such property since we can't make 25 with dimes, right? We can't make 25 with dimes, and that's kind of weird because that means there are some situations where we want to use dimes instead of quarters. Right? Which means that we don't follow the rule of picking the largest coin to use. Give me a smiley face in chat if you feel good. If this feels like this clicks for you. I didn't give you a formal proof. I just gave you an intuitive sketch, right? And obviously, it's not what you would want to say to a GSU computer science theory professor when you're trying to explain this, but we're not here to impress computer science professors. You know, you don't have to impress me. You don't have to impress anyone else. You just have to learn this stuff so that you can program real good, all right? If you want to go and prove that this works, go ahead and check your textbook. There are some proofs that you can see of some previous examples that we covered, the scheduling activity schedule one and the serving customers one. There are some mathematical proofs in your book in chapter 16. All right, so why do we care? We just spent a lot of time harping on coins, and that wasn't really like super interesting for a lot of us, right? I wouldn't say that this is the most interesting way to spend your time. So why are we focusing on this so much? Let's go ahead and take a look. If we have a greedy algorithm, let's say this one here, and we want to code it out, what would that look like? Let's see, public static int make change 1, let's say, int n. So this is solving the previous section's problem. I'll even move it back one step so that you can follow along. So this is the first problem that we were trying to solve. We're just going to translate this into actual code, right? So actual code actually gives us a neat trick to do this. We don't actually have to repeatedly subtract 25 like we did by hand. There is a operation that takes a single step that will allow you to automatically count up the number of quarters necessary in order to compute this. So take 10 seconds to think for yourself, which operation am I talking about while I code this out? All right, what do you think I'm saying here? Like, what do I have to put here in order to actually figure this out? Question mark if you're not sure. Otherwise, give me your best guess. Okay, a lot of people are saying mod, some question marks. What we want here is actually integer division. So in other words, n divided by 25 is integer division, skip the remainder. Right? If we just say the number of coins change, the amount of change we want to make divided by the 25 mark, this gives me the number of times we're going to correctly use a quarter to bring down my change. All right. And then if we want to change the n now has to be reduced, right? We can say n is equal to n mod 25. Right? What is the remainder? The remainder becomes the amount of change we want to make from there, right? So we do this one more time. That was for quarters. Now we're going to do this for nickels. N divided by 5, right? Handle nickels case, and we have something very similar in mod 5. Now at this point, here's a question for you. What does n represent at this point? What's the max n can be here? I'll give you 10 seconds to think about that for yourself. What's the maximum amount that n can be after we did these operations? And what does it represent? Go ahead and type in chat if you have it. Right? This should be 4. 4 is the max, and it represents the number of pennies we need to use. Right? If we went ahead and used all the quarters and we used all the nickels, then all that's left is to use the pennies. In other words, we can return the number of coins plus n, which is the number of pennies, and then we're done. All right. Now, what was the runtime of this algorithm? Right? We did some math. Literally, every single step was just math, right? And we know math is cheap. What's the overall runtime? Overall runtime is O of 1 here, because all we did was a bunch of integer operations. We did some division, we did some modulo, which is all very cheap. The first problem here can be solved in constant time. The next problem, if you didn't know how to solve it, the next problem would literally take O of n squared, which is really expensive. The make change 2 I'm thinking of we'll try every single possible combination of coin usage to make change for n. This will lead to an O of n squared, 2 to the n approach, which is really slow. Previously, I showed you the code for this in previous sections, but then I realized I wrote the wrong code, so I have to go and fix the code. I'll include the code when I upload this lecture by tomorrow. But this is, as you can imagine, really slow. There are faster ways to do this. We can get it down to like linear time, but that's still worse than O of 1, right? So what I'm saying here is, why do we care? Make change 2, when we changed nickels to dimes, we have to come up with an algorithm that takes exponential time, right? As we increase the size of n, it takes longer and longer by a drastic amount in order to solve the problem. Whereas for the first make change that we tried to solve, it literally only takes a constant amount of time. It doesn't matter if we have n is equal to a billion, it's still going to take like less than a second in order to compute this. Whereas make change 2 will literally take minutes on a modern computer. That's why we have nickels in real life. Yeah. I'll laugh at that. That's pretty good. All right. So to conclude, when do we use greedy? When the locally optimal choice leads to a globally optimal solution. In other words, when the two properties on the yellow slide are satisfied, then greedy will be an efficient algorithm to produce an optimal solution. Alternatively, when you just need a solution that's good enough, greedy will always be fast. It might not always be optimal, but it'll always be fast. Let me give you an example. Do you really want to spend your time at like Publix picking the perfect avocado, picking the perfect produce? Or do you just want to pick the one that is like good enough, it doesn't have any bruises, and then you leave, right? Or do you want to spend your entire life picking the perfect vacuum cleaner so that, you know, there's no cat hairs and it's relatively cheap and it's really going to last forever and you never have to buy another vacuum cleaner? Or you just find the one that's on sale that takes care of cat hair and then you move on with your life? You don't want to pick the move that's perfect in chess because you'll be there analyzing the board for hours and hours, but you only have 2 hours total to complete your chess move. So you have to go ahead at some point and stop and pick the best one you can find that's good enough in order to get you to a better position. If you are getting a rideshare app, whether it's Lyft or Uber, they don't spend the time picking the perfect driver. They just pick a driver that's 4.5 and higher and will get you from A to B safely. Right? They don't pick the best person ever or the best driver ever. You're not getting a chauffeur when Uber comes in. They just pick one that's nearby, that has good ratings and will drive you safely. And there you go. Right? So this happens a lot in industry, and we're going to see this actually in approximation algorithms, which is one of the last things we'll learn in this class. In general, it's easier to prove that you shouldn't use greedy. Just come up with a greedy approach and then find a counterexample, like when we had to make change. All right. Let's go ahead and do takeaways now. Greedy algorithms just pick the next obvious thing to build up our solution. For certain types of problems, greedily generated solutions are optimal and have algorithms that generate them that are super efficient, right? The O of 1 case like we saw before. Typically with greedy, we'll be sorting something first. So we had to go and pick the least waiting time customer to serve. We had to pick the lecture that was scheduled earliest, that ends earliest. We had to pick the coin that had the biggest amount. So there's always some sort of ordering that's either explicit or implicit in your code. And in order to decide when greedy won't work, all you have to do is pick a counterexample. So find a greedy algorithm and then prove that it doesn't work by finding the example where it breaks down. And proving when a greedy approach will work requires making a formal proof, which we're not going to do in this class. Because I want you to focus on other things. I want you to focus more on the programming than the theory, right? So general intuitive sketches for that sort of problem will be fine. That's all we had today. Thank you so much for your time. If you have any questions or concerns, feel free to ask now. But we are done officially for today. There are office hours right now. So if you have more questions, feel free to ask, all right?